Right, everyone, let's get started. Is that a bit loud? I'll try not to shout. Okay, everyone, we're up to page 20 of the notes. And has everyone got a copy of the notes now? I do have more copies of the notes, if you haven't got them. Okay. Right, as usual, before we look at the new material, we're just going to have a quick recap of what we've done last week. So, last week, we finished off the measures of dispersion. Okay, so if location is size, what's dispersion? What's that short word beginning with S that we think of when we hear dispersion? Spread. Okay, now your measure of spread might be quite basic. Okay, the most basic measure of spread, max minus min. What do we call that? The range. Okay, so the range, a drawback of it is that it's not very stable. If your extremes are unusual, if your dataset contains outliers, the range won't be particularly useful. So, a statistic that is more useful, more robust than the range would be the interquartile range. I should have put the dot cam on, then you'll know what I'm talking about. Okay, so this is what I was talking about. The range, max minus min. What about the interquartile range? How would you work it out? Upper quartile minus lower quartile. Okay, so it's just the range between the quartiles. Now, what about if you want to use all of the data but measure spread? Okay, you'll need the variance or the standard deviation. Okay, now what is the relationship between the variance and the standard deviation? How are they related to each other? They both measure spread. Okay, but what is the relationship between the variance and the standard deviation? The square root. Okay, the standard deviation is the square root of the variance. Okay, what is the advantage of using the standard deviation over the variance? Think about units of measurement. Okay, so out of the variance and the standard deviation, only one of them is measured in the same units as the raw data. Okay, so if you're looking at coastal wind speeds in miles per hour, okay, you might calculate the variance or the standard deviation, but there's only one of them whose units would be miles per hour. Which one is it? Almost right. It's the standard deviation. Okay, why is that? How do you work out a variance? What do you need to work out before you work out a variance? Yeah, before you work out the variance, you work out the mean. Okay, you subtract the mean, from each value, that gives you a series of deviations. Okay, what do you do with these deviations? You square them. Why do you square the deviations?
To avoid negatives.
To avoid the negatives. Okay, we then sum the squared deviations, work out the average, but we must do the opposite of squaring, square rooting, to return to a statistic that is measured in the same units as the raw data. Okay, so that's measures of dispersion. Now, what about graphical displays? Okay, we've got histograms and we've got box plots. Okay, what data type do you need to produce histograms and box plots? Would it be quantitative data or qualitative data? Okay, I'll just make this a bit larger. Okay, I've got a mini-tab project here in column 1. Can you all see this at the back? We've got some wind speeds. L1 is just location 1. So, what data type is this?
Quantity.
This is quantitative, okay, and to be a bit more specific, it's continuous rather than discrete. So, for column 1, we might produce a histogram. Okay, so in column 1, in terms of the sample size, the number of observations, it's 1,000. Okay, so at location 1, we have 1,000 wind speeds. And what do we know about those 1,000 wind speeds? If the data type is continuous. If the data type is continuous, those 1,000 wind speeds will all be yeah, I mean, the first wind speed is 19.5712 miles per hour. Okay? So think to yourself, will that exact wind speed have occurred again? It's possible, but theoretically, how many decimal places can you measure to? If the variable is continuous, then theoretically, you can measure to a limitless amount. So therefore, even if 19.5712 has occurred again, that's just the data to 4 decimal places. Okay? You can measure to any number of decimal places. So when a variable is continuous, okay, no 2 values are actually the same. Okay, so I've produced a histogram. And we know from our computer practical, what the histogram tells us, don't we? I've hovered my cursor over one of the bars and it says value equals 69, 19.9 to 20.1. What does it mean? It means that 69 of the wind speeds are between 19.9 and 20.1. Okay? What else can we say about the data? Okay, what did we talk about in the computer practical last week? Would you agree that this histogram is fairly symmetrical and fairly bell-shaped? So because of that, what can we also say about this data in terms of distribution? There's a word beginning with N that I'm thinking of. The normal distribution. Okay? So location with size, dispersion with spread, distribution is shear. Okay? This shape, symmetrical, bell-shaped. That makes us think the normal distribution. Now, that's the histogram, but what histograms are not very useful for is allowing you to make comparisons between groups. Okay? So if we wanted to compare the wind speeds at location 1 and location 2, then much better than comparing 2 histograms would be comparing 2 box plots. Okay, we can quickly see from box plots that the wind speeds are much quicker at location 1. Now, histograms, box plots, the data type you need would be quantitative, and here it was continuous. Now what about column 3 and column 4? Okay, so we're looking at the origins of ships. UK, Europe, Africa, North America, and other. So what data type is this that we've got in column 3? It's not quantitative, it's qualitative. And to be more specific, is it nominal or ordinal? Nominal, because there's no logical order. Now, a graphical display that we could produce would be a bar chart. Okay, now we said last week that this reminded us of, the bar chart reminds us visually of the histogram. Would you all agree? There is a similarity, frequency on the y-axis of both. Okay, you see vertical bars, but a visual difference would be that's right. With histograms, visually, okay, you don't see gaps between the bars unless you've got outliers. But with bar charts you do, and it comes down to the data type. Okay, continuous for the histogram. For the bar chart, it's qualitative, and here it's nominal. So I want you to think of that interpretation that we made from the histogram. What did we say? If the histogram is symmetrical and bell-shaped, what's our conclusion? The data is normally distributed. Okay? Now, think of the bar chart. Okay, I want you to imagine that this bar chart goes like this. Okay, so I want you to imagine that the bar for the UK is much smaller and the bar for Africa is much bigger. Europe a bit smaller too. So I want you to imagine that on the bar chart it looks like this. Okay, why would it be wrong to say this data is normally distributed? It's not continuous, is it? It's not a quantitative variable. So if your bar chart looks symmetrical and bell-shaped, well, that would just mean that Africa, okay, is the biggest origin, the largest origin for these ships. And Africa, of course, doesn't have to be in the middle. It could have been on the left. The variable is nominal. Okay, so what can we spot from a bar chart? When you look at a bar chart, what can you immediately see? I'm thinking of one of the averages that begins with M. Which average is particularly useful for qualitative data? The French word, mode, fashion. Okay, the most fashionable origin of the ships would be Europe. Okay, so when you're looking at a bar chart, you can see the mode. It's just the tallest bar. Now, the discussion item this week, what was it? There's another chart that looks nothing like a bar chart, but it is very similar. And what was the answer? Gideon got the answer? Where's Gideon? Well done, Gideon. Okay, pie charts. Pie charts look nothing like bar charts. Would you all agree? However, they are very similar because the tallest bar on a bar chart is the mode. How would you see the mode from a pie chart? Just the largest slice, yeah? Okay, good. While we're on that topic, can anyone think? Can anyone think what a bar chart would look like of the wind speeds at location 1? So the wind speeds at location 1, how many observations were there? 1,000. So the question is, what would a bar chart look like of the 1,000 wind speeds?
Next axis will be 1,000 observations with the frequency of 1. Will be 1,000 equal bar.
Well done. Okay, the wind speeds, that's a continuous variable. Okay, so the wind speed, the 1,000 observations were all different. So if you produce a bar chart of the 1,000 wind speeds, okay, there are 1,000 different wind speeds, all with a frequency of 1. So can you all see it's pointless producing bar charts of a continuous variable? And in a similar way, if you produced a pie chart, you would have 1000 slices, all with the same angle. Okay, so that was graphical displays. And what else did we cover? Okay, we talked about probability. And we said that probability is a relative long-run frequency. We mentioned the multiplication rule. Okay, this was the multiplication rule that you've got in your notes. But when can we use the multiplication rule? Only when events are independent. Okay, so I think our marine example was tonnage greater than 1,000, crew greater than 10. Those events would not be independent. Okay, the size of the ship would have some bearing on the size of the crew. Okay, so you wouldn't be able to use the multiplication rule. We also covered the addition rule. Okay, so if you're asked in a question, what is the probability of event A and event B occurring? Okay, when you hear that word "and," that makes you think the multiplication rule. But if you're asked the question, what is the probability of event A or event B occurring, that makes you think of the addition rule. And finally, as well as those rules, we talked about distributions. Okay, so we've got distributions for discrete variables when we're dealing with counts. Okay, there was the binomial distribution and the Poisson distribution. And finally, we finished off with distributions for continuous variables. Okay, and there is one that we're going to focus on. Out of these four, there's one that we will really focus on this course, because there are so many statistical tools and techniques that assume the data has this shape. Which one is it? Which is the most famous distribution of all? The normal distribution. Okay, so if someone asked you what the normal distribution looks like, hopefully you would describe its basic shape by saying it's symmetrical and it's bell-shaped. Now, which graphical display informs you of that? We know it's the histogram, don't we? So, what else can we say about the normal distribution? I'm just going to show you a page from Wikipedia, 6895.99.7. Okay, it's a rule. Okay, it's a rule that refers to normal variables. What does the rule tell us? Okay, if you look at this this picture here. Okay, the normal distribution has many properties. Okay, as well as it being symmetrical and bell-shaped, the mean. Where does the mean lie for a normal variable? In the middle. Okay. Now, what about 68? What does this number mean, 68? Yep, 68% of the data will lie within plus or minus 1 standard deviation from the mean. So therefore, 95% means 2 standard deviations, and finally 99.7% would be 3 standard deviations. Okay, we can never say where 100% of the data is because it's a continuous distribution. So theoretically, any value is possible. Okay, so something that we only briefly mentioned in the computer practical last week was in your research into marine science, marine engineering, you will come across samples and populations, okay, and we covered those definitions in lecture 1. Now, we know that the measure of location, the average, that uses all the data, okay, there's only one average that uses all the data, it's the mean. Now, if you're working out the mean of a sample, what symbol do you use?
X bar.
X bar. Whereas if you work out the mean of a population, you use
1.
a Greek letter, okay, mu or me, okay, looks like this. Now, what about the standard deviation, okay, a measure of dispersion? It uses all the data, but what about the symbols? Okay, S for a sample, and what about a population? Okay, for a population, it's lowercase sigma. And finally, just to finish that off, what about the variance? Well, we know the relationship between the standard deviation and the variance, the standard deviation being the square root of the variance, so therefore sample variance must be S squared, and population variance must be sigma squared. So what's our rule of thumb here that we can see developing? If it's a population characteristic, if it's a true value, what alphabet are we using? Greek. Whereas if it's a sample statistic, we use the Roman alphabet. Right, so with that in mind, what I would like you to do is just read these first 2 paragraphs of the notes on page 20. Okay, so you're just reading the first 2 paragraphs on page 20. Okay, so with the techniques that we're going to look at next, there is an assumption, and the assumption is that the population from which the sample was drawn was normally distributed. Okay, so it really is a key distribution. Now, what is the motivation behind confidence intervals? Did these 2 paragraphs make sense to you all? Would you all agree that in your research you would never be studying populations? Okay, it's almost always the case that we study samples instead. However, why do we actually study samples? Because ultimately we're interested in the populations from which they were drawn. Now, what I would say is this. The definition of sample is, of course, any subset of a population. However, a sample needs to be good, doesn't it? And by good, we mean representative. Okay, you can ensure your sample is representative by taking it in a random way. Now, assuming your sample is representative of the population, your sample statistic, okay, your sample statistic will always be your best estimate of the true value. Okay, so does it make sense to everyone that X bar will be our best point estimate of mu, or me? So, I want you to imagine that in Newcastle, okay, we're interested in the average house price. Okay, and we randomly select two houses. Okay, one house is worth £100,000 and the other house is worth £400,000. Okay, we know the sample mean would be £250,000. So would you all agree that £250,000 would be our best estimate of the true mean? However, is it a precise estimate based on what I've told you? Can you think of any reasons why that would not be a precise estimate? Sample size, okay? The sample size was just 2. And also, would you agree that there's a lot of spread there? One house is worth £100,000 and the other house is worth £400,000. So for those two reasons, small sample size, but also large dispersion, that will not be a precise estimate of the mean. Whereas if we go to another city in the UK and we randomly select 100 houses and they're all worth, more or less, £250,000, well, the sample mean would still be £250,000, but now it would be a more precise estimate of the true mean. Okay? So, why do we need confidence intervals? Well, I could say to you, I've just done a study in house prices in Newcastle, and I believe that the average house price is £250,000. It might be the case that I've looked at just two houses, and one was 100k and one was 400k. If I say to you, I'm 95% confident that the true mean house price in Newcastle is between £50,000 and £450,000, you would then know that actually I don't have a precise estimate. Okay? So, how do you work out a confidence interval? Okay, can you all see this okay at the back? I'll read it in your notes. We're still on page 20. So, you would need to work out, if it's a confidence interval for the mean, you would need to work out the sample mean, and you would need to work out what else? What do we know S stands for? S stands for the standard deviation, doesn't it? Okay, so you need to work out the sample mean, you need to work out the standard deviation, and you're also going to need, okay, if you were doing this by hand, you won't do this by hand, you'll use Minitab, okay, but if you were doing it by hand, you also need a coefficient. You also need a coefficient that comes from statistical tables. Okay, the coefficient relates to the level of confidence you're working to. So in research that you've written or read, has anyone ever produced or seen a confidence interval? Okay, well, there is a standard level of confidence that we work to. Okay, there is a standard level of confidence that we work to. What is it? The standard level of confidence is 95%. Does that make sense to you all? That you want confidence to be high? If you're 95% confident about something, there's only a 5% chance that you're wrong. Okay? So we want to minimize that error. 95% is a common standard to use. So if you're interested in the theory, well, you'd need to use tables to read off the coefficient. Okay? So you think about the error. Okay? If you're 95% confident, what's the error? What's the chance you're wrong? 5%. So you would need to look at the table that you've got on page 21. Okay, so this is just a subset of the table, okay, because the coefficient that you pick, it will depend on the level of confidence that you're working to, but also your sample size. Can you all see that Greek letter there? Looks like an italic V, but it isn't. It's another Greek letter. What is that Greek letter? Any of our Greek students want to help me? Nu? Okay, so that letter there, that Greek letter there, is nu. Is that right? Ni. Yeah. So if you see that, okay, if you see that, the important thing isn't knowing really what the Greek letter is. It's more important to know what it represents. So just like mu, me was the mean, sigma was the standard deviation, this letter is the degrees of freedom. Okay? Okay, that letter there is known as the degrees of freedom. Okay, so it's known as the degrees of freedom, but degrees of freedom are determined by sample size. And if it's only a one sample problem, the way that you work out degrees of freedom is very simple. It's just n minus 1. Okay, so what if your sample size was 16? Okay, what would the degrees of freedom be? 15. So therefore, if you're working to 95% confidence, you would look at the column that starts at 5% and read down to 15 degrees of freedom. So the coefficient would be 2.131. Okay? Eventually, for very large sample sizes, what's the coefficient? What do you see at the bottom of that column? 1.96? Okay, that actually relates back to the normal distribution, because what did we say before about 95%? 95% within plus or minus 2 standard deviations. Okay, that's just an approximation. To be exact, it's 1.96. Okay. So just a new data set there. Okay, new data set there. We're looking at box weights, but remember that there's many applications for these techniques in marine science. This could be ship weights. But if it's box weights, let's say that the mean is 500 and the standard deviation is 2. Okay. In your notes, I want you to assume the normal distribution. Okay, if you're told that a variable is normally distributed with a mean of 500 and a standard deviation of 2, okay, I want you to sketch the curve in your notes. Okay, I want you to use the 99.7 part of the rule. Okay, mean 500, standard deviation 2. You should be able to sketch the normal curve. Remember, 68, 95, 99.7. Okay, so what did you all get then? If we're using the 99.7% part of the rule, what does that tell us? The 99.7% of the data is within... Well, you need to multiply the standard deviation by 3, don't you? And what's our standard deviation? 2, so that gives you 6. So where will the middle be? 500. You take 6 away to get 494 and add 6 to get 506. Does that make sense? Okay, that's just using the rule. What about 95% of the data? You would multiply the standard deviation by 2, that gives you 4. Take it away, that gives you 496. Add it and you get 504. So, the command that you're going to be using in the computer practical for your confidence interval, okay, the command that you will be using in the computer practical, because you won't do this by hand, but Minitab would be using this equation here. Okay, so you do have the equation in your notes. Okay, you'd be crazy to use it though when Minitab does it for you. You'll be doing this in the computer practical. Okay, stat basic statistics, 1 sample T. And what we'll do here is we will just use some summarised data, okay? We won't use the raw data that we've got on column 1 there. I want you to imagine that we've taken a sample of 16 boxes, and the sample mean to a certain number of decimal places is 500 grams, and the standard deviation is 2 grams. Okay? The important thing is always being able to interpret output. So, take a look at this output here, and I want someone to help me interpret the numbers in brackets, because that's the confidence interval. Okay, so what is the interpretation? What is the interpretation of those 2 numbers in brackets? It's a 95% confidence interval. But if you had to describe it in words, okay, part of your project will be critically analysing a research paper. Okay, so confidence intervals might crop up. You'll need to interpret them. Okay, we've got a confidence interval there. How do we interpret it? Anyone want to have a go? Well, what was our sample size? 16. The sample mean, what was it? 500 grams, okay? So, 500 grams, remember, is the sample mean. But we can use the standard deviation and the coefficients from that table that I showed you to construct a confidence interval. We've got it there in brackets. What does it tell us? It tells us where we believe the true mean is. Okay? The incorrect interpretation, the one I thought you might make, is 95% of the box weights are between these two values. Because you've just worked that out, haven't you? I just said to you, imagine the mean is 500, imagine the standard deviation is 2. You used the rule, didn't you? That I showed you in Wikipedia. What did we say? 95% of the box weights, if the mean's 500 and the standard deviation's 2, would be between, can you all remember 496 and 504? Okay, that was the raw data. That's 95% of the box weights. That's different to these two numbers, isn't it? Because we're not talking about where 95% of the box weights are. We're saying we're 95% confident that the true mean lies between those two numbers. Does that make sense? Now, with these confidence intervals, with your own research, let's say you're looking at weights of ships rather than weights of boxes of cereal, what do you think you'd want? Do you want wide, imprecise confidence intervals, or do you want narrow, precise confidence intervals? You want narrow, precise confidence intervals, yeah? So, what affects the width of a confidence interval? Any guesses? I gave you a scenario earlier to do with house prices, and you said, that doesn't sound precise. Sample size affects precision, okay? The larger your sample size, the more precise the interval. Anything else? The spread, okay? Standard deviation. The more spread out the data, okay, the larger the standard deviation, the wider the confidence interval. And finally, the third thing that affects precision. Any guesses? You've seen the equation in your notes. Okay, we've talked about S, we've talked about N. What about T? What's T? T would be the coefficients from the tables that I showed you, okay? Because the level of confidence also affects precision. Can anyone guess how? As confidence increases, what happens to confidence intervals? Any guesses? As confidence increases, yeah, look at the table. As confidence increases, what's going to happen to the confidence interval? The confidence intervals actually get wider. An analogy would be, to make sense of it, because at first you might think, surely a 99% confidence interval is better than a 95% confidence interval. With 95% confidence, the chance you're wrong, 5%. 99% chance you're wrong, 1%. Sounds better, doesn't it? But if confidence intervals became more precise, as confidence increased, we would always just work to 100% confidence. Okay? So there has to be a drawback to increasing confidence. Think of it like supporting a football team. If you support a football team in a league of 20 teams, you could say at the start of the season, I'm 90% confident my team will finish between 5th and 15th. But you could say with 100% confidence your team will finish between 1st and 20th. Okay? So as confidence increases, the intervals just get wider. Okay, so in your notes you've got the example of the cuckoo's eggs that were laid in the robin's nest. A confidence interval for it, but it's just the procedure that we've already described. Okay? You work out the mean, you work out the standard deviation, you work to a certain level of confidence, and then you get an answer. Okay? But you wouldn't do any of this by hand, you would just use Minitab. So, what about what about hypothesis tests? Has anyone heard of them? Hypothesis tests or statistical tests? They're actually very closely linked to confidence intervals, as you'll see. Now, again, what I would like you to do, just for the next minute, is read those first two paragraphs. Okay, you're going to see shortly that these tests are very closely related to what we've just done, confidence intervals. Now, with a one sample problem, there will be a certain parameter under investigation. It might be the mean, might be the variance, mu or sigma squared. More commonly though, it would be the mean. So with a one sample problem, an example of a null hypothesis okay, an example of a null hypothesis on the mean could be this, just what you've got in the notes there. Okay, if it's a one sample problem, an example of a null hypothesis would be the true mean equals some value. So the true mean equals, let's say, 2.7. And as well as the null hypothesis, which has the shorthand notation H0, you have an alternative to the null. Okay, the alternative hypothesis, shorthand notation HA. Now, if you have no prior evidence either way, it makes sense to make your alternative simply the opposite of the null. So the null here, the true mean equals 2.7. The alternative, the true mean, doesn't equal 2.7. And the hypothesis test, whichever test you carry out, they all result in a p-value. Okay? They all result in a p-value. So in the computer practical that we'll do shortly, we'll focus more on two sample tests. So I want you to imagine that we've got boys and girls, okay, 10 boys, 10 girls, and they've taken an exam in maths. Now, if you're only interested in these 10 boys and these 10 girls, all you would need is to work out the means of those columns, and whichever is the biggest mean, you've got the answer. They're doing the best at maths. But in terms of inferential statistics, you're actually interested in the populations from which these samples were drawn. Okay, so that's why you need to carry out the appropriate technique. Now here it will be the two sample T. Can anyone help me write down the null? What does the word null mean to you? Null, N-U-L-L, nothing, zero, no difference. So the null here would be, we've got boys and girls, males, females, so the null would be that they are equally as good at maths. Does that make sense? The true means are the same. M for males, F for females. And what would the alternative be? If we make the alternative simply the opposite of the null, would you all agree it would be that? Does that make sense? Okay, so that's your null, that's your alternative for the 2 sample t. Now, another test that you'll do in the computer practical, I'll just mention it because you will do it in the computer practical. Can you see here that it looks at first like we've got the same data as here? Would you agree that on both occasions you see, you know, math scores taking up 2 columns? But can you see here that the samples are unpaired, whereas here the samples are paired? Okay, this was 10 boys and 10 girls. Okay, that's 2 independent samples. What about here? What have we got here? 10 boys, and they take an exam in maths in year 1. And what happens in year 2? The same 10 boys take another exam in maths. Okay, so that isn't the 2 sample t-test. What's it called? The paired t-test. Okay, so just as we finish, I'm going to run one test for you. Okay, I'm going to run one test for you in Minitab so you can see it. And I want you to help me to interpret Okay, so I've got a 2 sample t here. It's not the paired t-test. It's a comparison of 2 samples that are unpaired. Now, there is an assumption of the 2 sample t that you'll see in the computer practical. The assumption is that the dispersions are similar. Okay, so you'll go to options and you'll tick assume equal variances. But before you do that, you should actually work out the standard deviations, variances, check that they're quite close. And you know, always produce graphical displays in conjunction with your test. If you want to compare 2 groups that are independent, makes sense that it's the box plot. So, who's doing the best at maths? Is it the boys or the girls? Would you all agree the girls are doing a bit better than the boys? Okay, but that's just the sample data. We're now trying to make an inference about what's going on in the wider populations. How do we do that? What do we look for? We look for the p-value. What's this one? 0.401. So what should our decision be? Well, in this table, it's an important table, it's in your notes. Okay, we'll talk about it more in the computer practical. This is how you interpret the p-value. Take a moment to look at it. Right, everyone, so any test that you do, whether it's a 1 sample t, a 2 sample t, a paired t, and even the more complex ones that we'll do later on, they all result in a p-value. And this is how you interpret them. If the p-value is low, that's evidence against the null. Okay, the lower the p-value, the more unlikely the null is. Okay, so that's it for lecture 3, and we'll now do the computer practical upstairs.
I've got lots to bring, so I'm not sure.
No, okay, thanks. It's all right.
Yeah.